atomic spectrum of hydrogen spectrum. Atomic spectra or line spectra we can say, or line spectra of hydrogen is obtained by passing the light emitter, is obtained by passing the light emitted from the discharge tube containing hydrogen gas, from the discharge tube containing hydrogen gas at low pressure through a spectroscope. Okay, low pressure through a spectroscope. Okay, so we can see atomic spectra, that is different lines of hydrogen atom can be obtained. So what will happen here? Electric discharge is passed through the gaseous hydrogen. Okay, so what will happen? Hydrogen molecules then dissociate into hydrogen atoms, and energetically excited hydrogen atom produce or emit electromagnetic radiations of different frequencies. So we can see different lines in the spectrum. Okay, so the spectrum consists of large lines of different frequencies. Okay, large lines of different frequencies. Okay, so these lines in the emission spectrum of hydrogen is grouped into 5 series. Okay, these lines are grouped into 5 series, which are the Lyman series. So they got its name after the discoverer of each lines. Okay, so first one Lyman series, then Balmer series, third one Paschen series, bracket series, and fund series. Okay, these are the 5 series. Okay, so all these lines grouped into 5 series. These are the 5 series. Okay, so these are the different series of lines. Okay, this is a diagram showing the transition of electrons. Okay, so in the case of Lyman series, N1, the first the ground state is the N is equal to 1 will be the ground state. Okay, so from different excited state, the electron transition takes place to this N is equal to 1 state, this ground state. Okay, so such transition, such series of lines are called as Lyman series. This is the first one. Okay, so here N1 is equal to 1. Okay, and N2 is equal to higher level, next higher levels 2, 3, 4, etc. From which to N1 is equal to 1 the transition takes place, and the spectral region of this Lyman is UV region. Okay, now second one is Balmer series. Similarly, the transition takes place from different higher energy levels to N is equal to 2 energy state. Okay, such series are called as Balmer series, and the spectral region is visible region. Okay, so N1 is equal to 2, into which the transition takes place from different higher energy states like 3, 4, 5, etc. Similarly, in the case of Paschen, the lower energy state is N is equal to 3. From different levels 4, 5, 6, etc. the transition takes place, and this is in the IR region. Now bracket N1 is equal to, that is the lower energy level is 3 in the case of Paschen, and from 4, 5, 6 this transition takes place, and spectral region is IR. Now the bracket series the N1 is 4, that is the lower energy level is 4, and from 5, 6, etc. energy levels the transition takes place, and this is in the spectral region, IR region. The spectral region is in the IR region. Now, last one is fun series. Here N1 is equal to 5. See, N1 is equal to 5. So, into which the transition of electrons from different excited states, that is 6, 7, 8, etc. the transition takes place. And this is in this, the spectral region is in the IR region. Okay, there is one more series that is called as Humphrey series also. Okay. Here, the transition takes place to the level n is equal to 6 from different different higher energy levels. Okay, these are the different series. Okay. So next, Rydberg. In 1890. Rydberg in 1890 gave a general formula for the wave numbers of different lines. General formula for wave numbers of different lines. Okay, numbers of different lines in the hydrogen spectrum. That is different series, 5 series of spectrum. Okay, so this general formula is applicable to all the 5 series. So the equation is 1 by lambda, or we can say nu bar. This is the wave number. Wave number is equal to R, which is the Rydberg constant, by 1 by n1 square minus 1 by n2 square. And we know n2 is always greater than n1. Okay, R is the Rydberg constant, which is equal to 109677. Okay, centimeter inverse. This much will be the value of Rydberg constant. Okay, so using this we can do we can calculate the wave numbers of different lines in the spectra, like Lyman series, Balmer series, etc. Okay, line spectra becomes complex in the case of heavier atom. This is in the case of hydrogen atom. Different lines are obtained. It becomes complex in the heavier atom. So for other hydrogen-like species, he introduced one more factor, that is nu bar is equal to Rz square into Z is atomic number. Okay, minus 1 by n2 square. So this will be in the case of other hydrogen-like species. Okay, so this much about the atomic spectrum of hydrogen. Next, let us do one problem based on this formula. Okay. The problem is calculate the wavelength of the first and last line in the Balmer series of hydrogen. Okay, so the transition takes place from different exciton energy states to the level n is equal to 2. So first we can write the formula 1 by lambda, or nu bar will be equal to R, which is called as the Rydberg constant, into 1 by n1 square minus 1 by n2 square. Okay. Now, in the case of first line, 1 by lambda will be equal to R. R is equal to 109677 centimeter inverse. Okay. So, 109677 into, we know n1 is 2. And first line is obtained from n is equal to 2. From n is equal to 3 to n is equal to 2. So n1 is equal to 2 and n2 is equal to 3. Okay, so from 3 to 2 transition takes place. So n2 is equal to 3 square. So 109677 into value is 5 by 36. This is 1 by lambda. Okay, so lambda will be equal to 36 by 5 into 109677. Okay, so after doing the calculations, lambda will be equal to 6.565 into 10 raised to minus 5 centimeter. So actually lambda is in nanometer. So we have to convert it. First convert it into meter. So this will be 6.565 into 10 raised to minus 7 meter. So by conversion this we have to convert it into nanometer. So 656.5 into 10 raised to minus 9 meter, or we can say, so 1 nanometer is equal to 10 raised to minus 9 meter. So 656.5 nanometer. This will be the answer, lambda, for the first line. Okay, 656.5 nanometer. Okay. So next part of the question is, for last line, how can we calculate last line? In the case of last line, same, n1 will be equal to 2, but n2 is equal to infinity. So we can substitute in the formula. We know 1 by lambda or nu bar is equal to r into 1 by n1 square minus 1 by n2 square. This is equal to, the value we can substitute, or r is equal to 1 by 2 square minus 1 by infinity square. This value is 0. Okay, so this is equal to 109677 into 1 by 4. Or we can say lambda is equal to 4 by 109677. Okay, the value is 3.647 into 10 raised to minus 5 centimeter inverse. This is centimeter, that is nu bar is centimeter inverse. So lambda will be centimeter. Okay, so this will be equal to 3.647 into 10 raised to minus 7 meter, that is 364.7 into 10 raised to minus 9 meter, or this is equal to 364.7 nanometer. This will be the value. Okay.